So to solve this problem, I'm looking at two boxes connected by a rope, and it tells me a couple things. First off, it tells me that I'm going to do two free body diagrams, one for the box on top and one for the box on the bottom. So I'm just going to label these as just box 1, and I'll call this one box 2, just keep them separate. And then I also have a rope attached between the two boxes. So the tension in the rope is going to be the same on the top as it is on the bottom. So that tension will be the same mathematically in my equations. All right, so let's start with the free body diagrams. I'm going to start with a pair of free body diagrams. I think I have to write a little bit smaller than usual. Let's just look at the top box so I can figure out what's going on here. So if I look at the top box, I'll start with my free body diagram here. Um, Now, the boxes are not accelerating, just hanging from the ceiling. That's another thing they have in common. Whenever you have objects attached to the rope, not only is the tension between them the same mathematically, but so is the acceleration. So whatever the top box is experiencing, the bottom box in this case, or the other end of the rope, is experiencing the same thing. So in this case, an acceleration of 0. All right, what do I have? On the top, I've got tension going up. Attached to the ceiling on the top box, I'll call that T1. And then going down, I've got two things. I've got T2 on the bottom going down. So there's T2, and I'll call this uh, M1G, or yeah, and M1G is the weight of the top box. All right, so there's my free body diagram. And now, let's see, I'm pausing, thinking about where I want to sum up my forces. I'll sum up my forces in the x direction. That doesn't do anything. Sum up the forces in the y direction. Well, it's not changing speed up or down. In fact, it's not moving at all up and down. So I'll say all the forces up equals all the forces down. So all that's equal to 0. All the forces up on my free body diagram is T1. Two forces are going down, so minus T2 and minus M1G. That's the weight of the top box. Great. Let's do another free body diagram. And this time we're going to do the box on the bottom. So I'll just call this the bottom box. Bottom box. Awesome. And I'm going to erase that for a second. Okay, bottom box. Now there's my, ooh, let's change the marker here. Bottom box, 1, 2, 3. Let's do, doesn't really matter, I guess. So there's the free body diagram for the bottom box. Now the bottom box has tension going up. So there's my tension going up. Call that T2 because it's the same rope as the previous problem up there. Okay, connecting the two, so I want the same subscript. And going down, I'll have the mass of the bottom box. So that's going to be M2G. And then when I sum up my forces, let's see, where can I put all this? Yeah. I'll sum up my forces in the x direction. Okay, that's boring. That's equal to 0. Then I'll sum up the forces in the y direction. It's not changing speed, so that's equal to 0. Forces going up minus forces going down. Now, a couple things about this. I know that the T2s are the same because it's the same rope. That's why I gave them the same subscripts. So there are a couple of ways I can solve this. What I'm going to do is I'm going to take T2 and isolate it in the bottom equation for the bottom box. So T2 is equal to M2G. And then I'm going to put the value for M2G into the top equation for the top box. So the top box had the equation that said T1 minus T2 minus M1G, and all that was equal to 0. So now I'm going to replace that with, let's see, 0 is equal to, well, let's see, there are a couple of things I can do here. Let's, instead of doing that, let's do something a little different. Let's isolate T1. No, let's not do that. Let's just stick with this. So 0 is equal to T1 minus, and here what I'm going to do is I'm going to take what I said T2 is equal to, So I'm going to take this and I'm going to put it in for T2. So T2 is equal to M2G minus M1G. Hey, great. And now I can actually put in my numbers and figure out what T1 is. So T1 is equal to, if I move it to the other side of the equation, equal sign I mean, M2G minus plus M1G. So that's what T1 equals. Let's see. So I'm going to do one more thing. I'm going to say T1. I'm going to use the distributive property to pull G out just to mathematically make this look a little bit easier. No, I can't do that. And the reason why I can't do that is because it gives me the weight of the box. So the weight of the bottom box is 300 newtons. And see the top box, it tells me that is 20 kilograms. So I'll use mg for one and m1g for the other. Alright, so let's just erase this. Alright, top box is 20 kilograms. So that's going to be 20 kilograms times 9.80 meters per second squared plus, let's see, and the bottom box has a weight of 300 newtons. So from here, what I'm going to do is say that T1 is equal to the bottom box, which is 300 newtons. Now that is mass times gravity already. So that's 300 newtons. In other words, this is equal to 300 newtons when I multiply it together. And the top box is going to be 20 kilograms times 9.80 meters per second squared. And when I do that, I get that T1 is going to be 496 newtons. So that's T1. Now it's time to find T2. To find T2, what I'm going to use is my equation up, one of my other equations that are above. So T2, a couple choices here. T2, oh well, T2 is just equal to M2G. So M2G is actually 300 newtons. So if I just use this, then I can see that T2 is equal to 300 newtons because M2G is given to be 300 newtons.